Processing power dictates what we can actually build in the modern era of AI and computing. If the hardware can't handle the math, the software simply doesn't run. But when you're deciding where to spend your budget, you immediately hit a wall of acronyms: CPU, GPU, TPU. It is easy to get lost in the specs. Picking the wrong architecture has strict consequences. You will either bottleneck your entire project, or you will burn massive amounts of cash on highly specialized equipment you can't actually use. This chart plots the universal hardware trade-off. We're looking at task flexibility on the vertical axis and specialized parallel speed on the horizontal axis. You can't buy a single chip that maxes out both. Up here in the top left, we have maximum flexibility but low specialized speed. That is the CPU. Down in the bottom right, you get extreme speed but zero general flexibility. This is the domain of the TPU. Right in the middle is the GPU, serving as the crucial bridge between these two extremes. Because there is no universal best chip, building the right rig depends entirely on accurately diagnosing the rigidity of the work you actually need to do. Let's start with the Central Processing Unit, or CPU. Think of this as the mandatory mastermind of any computer. Physically, a CPU has a very small number of processing cores. Usually you are looking at between 4 and 24 cores in total, but its superpower is low latency. Those few cores are incredibly fast. They're engineered to handle highly complex sequential instructions, one right after the other. A CPU is like a highly skilled master chef or a Ferrari, extremely fast, capable of executing the most complicated tasks imaginable, but strictly limited to handling one or two things at a time. That makes it perfect for running your operating system, word processing, general logic, and managing databases. The limitation, however, is scale. If you force a CPU to do thousands of simple tasks simultaneously, like the massive math required for AI training, it creates an immediate bottleneck. So the CPU provides your indispensable foundation and ultimate flexibility, but it lacks the scale required for modern parallel processing. That brings us to the Graphics Processing Unit, or GPU. Originally built to render video games, it has become the undeniable backbone of modern AI. This comparison matrix shows why. In the architecture row, the GPU abandons the CPU's small core count for thousands of simpler cores. Moving down to the superpower row, the GPU's advantage is parallel processing, achieving massive throughput by doing thousands of calculations simultaneously. If the CPU is the master chef, the GPU is an army of 1,000 kitchen helpers, individually slower, but collectively able to process massive volumes of simple work instantly. You deploy GPUs for tasks that require sheer volume: video rendering, 3D gaming, cryptocurrency mining, and training localized machine learning models. The functional trade-off is autonomy. A GPU's cores are too simple to run an operating system on their own. They require a CPU to hand them instructions. The GPU acts as the critical bridge. It gives you versatility for creative media while delivering the heavy parallel muscle necessary for local AI workloads. Finally, we reach the Tensor Processing Unit, or TPU. This is a custom-built tool designed by Google strictly for machine learning at massive enterprise scale. At a hardware level, a TPU is an application-specific integrated circuit. It relies on what is called a systoleic array architecture. This architecture is engineered for one specific job, handling massive volumes of matrix multiplication and addition. That happens to be the exact math that powers neural networks. Think of the TPU as an automated pizza-making machine, or a bullet train. It achieves unbeatable speed and power efficiency, but it only runs on one highly restricted track. You use TPUs exclusively for deep learning inference and training massive AI models, like Gemini or ChatGPT. The trade-off here is total rigidity. It cannot do general computing. It can't run a video game, and it cannot chop vegetables. The TPU represents the ultimate specialization tax. You gain industry-leading AI speed, but you sacrifice all general utility to get it. So the question is, how do you actually apply all this data to decide exactly what you need to build or buy? This decision tree flowchart evaluates your options based entirely on your specific scenario. Question 1. Is your primary goal running standard software, basic logic, or an operating system? If yes, the chart points straight to the CPU. This maps to the everyday PC builder. If your tasks are sequential, Do not overinvest in parallel hardware. If no, we follow the chart to question 2. Do you need massive parallel processing for versatile tasks like rendering, gaming, and local AI? A yes here lands you on the GPU. For creators, gamers, and independent AI practitioners, this provides the best middle ground return on your investment. If the answer is still no, our final flowchart question asks, are you exclusively training massive deep learning AI models? And that leads us to the TPU. This is strictly for the enterprise AI developer, who is constrained by time and power scale and cares only about specialized performance. Keep the analogy in mind. Do not buy the industrial pizza-making machine if your actual daily workload occasionally requires you to chop vegetables. Successful hardware optimization is never about buying what is universally best. It is about practicing brutal honesty regarding the specific rigidity of your own workload.